Okay, class, in this lesson, you're going to learn to apply concepts of motion in one dimension. Now, one of the things that I wanted to kind of review in case you weren't aware, since if you're new to physics class, is that physics is a branch of the natural sciences that studies matter, energy, space, time, and most importantly, how all of those interact with each other. Okay, some of those key concepts will include matter, energy, force, and motion. And for today's lesson, we are going to focus on motion. Okay, and this is motion in one dimension. So when you think about a bird flying in the air, that's in 3 dimension. But today we're going to talk about 1 dimension. So for example, a car moving in a straight line, that is 1 dimension. Okay? So there are 4 conditions of movement. Okay? 4 conditions. Condition number 1 is that of time. And as we had defined in our earlier lesson, time is the interval between events or the measure of change. Okay? It's the interval between events or the measure of change. Now, the unit measure of time is typically in seconds. Okay? Or S. Sometimes it is done in minutes. That's in MIN. Or sometimes it's in hours, or represented by H. Okay? The most common will be seconds. Now, the second condition of movement is position. Okay? Position. Position can be positive or negative. Positive or negative. What you determine as positive or negative is arbitrary. The point is you have the ability to set those. For example, if I want to go left, that could be considered negative, and then therefore the opposite direction or to the right would be positive. Okay? Another example would be if I want to move up, that's going to be positive, and if I move down, that would then be a negative. Okay? So whichever direction you set as positive, the opposite direction will be negative. Now, there is a difference between distance versus displacement. Okay, we talked about distance. We know things like the distance of a meter, or a distance of a centimeter, or a distance of a foot, or a yard. Okay, or even a mile. Those are all distances. Displacement is a little bit different in that it is distance, which is the magnitude, but it also includes the direction. For example, a car drives 40 miles. That is just a distance. However, if you say that a car drives 40 miles going east, then that would be a displacement. Okay? And in physics, when we talk about the distance or displacement, we're talking about a straight line. So the beginning point to the end point, regardless of what happens in between. You could be going down, you could be going on curves, you can be going in a different direction, but at some point you're going to end somewhere. When the question is asked, what is the distance or what is the displacement, you're going to go from the beginning point and you're going to go in a straight line to the ending point. Okay, so let's take a look at an example. Let's say a car drives 30 miles east and then 40 miles north. What is its displacement? Okay, displacement. So that's the key right here. This tells me that our answer is going to need a magnitude, so a number with a distance, and we're going to need a direction. But let's go ahead and draw this out first. Okay, so let's say we have a car here. Okay, here's the car, and it drives east for 30 miles. So that is 30 miles. We're going to say 30 miles east. Okay? And by the way, this arrow that I drew is a vector. Okay? And this vector is important. The length of this vector is important because this represents 30 miles. Okay? And this direction tells me it's going east. So that means when we draw 40 miles north, this vector has to be longer than the 30 miles that I just drew. Okay? So this vector is going to be 40 miles, and this is north. Okay? In physics, it's really important to draw things out so you can see what's going on. And now we want to know what is its displacement. Well, the displacement is a line, a straight line from the beginning point to the ending point. Okay? So we want to know what this thing is right here. What is that length? Well, if you notice, this looks like a triangle, and this happens to be a right angle here. So we can go ahead and label that as a right angle. And so now we have a right triangle. Okay? So if you recall, to find this distance, the hypotenuse, we're going to use the Pythagorean theorem. Okay? Pythagorean theorem. And what does that say? C squared is equal to A squared plus B squared. Okay? So we're going to call this C is the hypotenuse. We'll call this, the bottom, A, and this B. It doesn't matter which is A and which is B, as long as one is A and the other is B. Okay? Solving for C, we have to take the square root of both sides. And so now C is equal to square root of, what is A? 30 squared plus 40 squared. Okay? And if you punch that into the calculator, or if you know that this is a perfect right triangle, you'd see that C is equal to 50. Okay? So what is our displacement? Remember, we need a magnitude and a direction. So my displacement is equal to 50 miles, and the direction is going to be northeast. Okay, this direction is northeast. 50 miles northeast. Okay, and so that is our answer for this example. Okay, so let's move on to the third condition. Third condition is velocity. Okay, now velocity is defined by the change in position over time. Okay, change in position over time. So let's go ahead and write that down. Velocity is equal to the change in position over time. Change in time. Okay, what this means is we're going to look at the position final minus the position initial over my final time minus my initial time. Okay, and then there is a difference between speed versus velocity. Okay, we are all familiar with speed. Okay, we talk about how fast a car goes or what the speed limit is on the freeway. And we often see the sign 65 mph, right? Miles per hour. But we really don't think about what that really means, miles per hour. But if you think about it, mph is really the same as miles per 1 hour. Okay? And what is miles? That is distance. That is my change in position, right? Change in position divided by time. Distance over time. This is my speed. Now, the difference between speed and velocity has the same difference as distance and displacement, in that speed just has the rate, okay? Velocity, however, has the rate, which is my magnitude, and direction. So a car could be traveling at 65 miles per hour east, so that would be a velocity. If we said that a car was traveling 65 miles per hour, then that would be speed. Okay, so let's take a look at an example. We have a car that traveled a total of 120 miles for 2 hours. What was its average speed? Now, most of you could probably figure this out in your head, but let's take a look at what the speed is mathematically. Okay, so we would say that speed or velocity was equal to the change in distance over the change in time, which was the final distance minus the initial distance divided by the final time minus the initial time. Okay, what was the final distance in this example? 120 miles. Okay, minus what was the initial distance at the beginning? It's 0 miles. And then the time, final time was 2 hours, and the initial time was 0 hours. Okay, so then this works out to 60 miles per 1 hour. Okay, so that is our speed. Okay, now we're going to move on to the fourth condition, and this is acceleration. Acceleration, if you think about it, is the rate at which an object changes its velocity. Okay, the rate at which an object changes its velocity. We all know what acceleration is, sort of. If you're in a car and someone decides to step on the gas pedal very quickly, you would very quickly also feel the back of the seat hitting you in the back, right? So the car is propelling you forward. That's acceleration. But what is really going on mathematically? Okay, acceleration, we're going to say A is really the change in velocity over the change in time, which is equal to the velocity final minus the velocity initial over time final minus time initial. Okay, so let's take a look at an example that applies this. A car reaches 60 miles per hour in 4 seconds. What is its acceleration? Okay, so let's take this formula and apply it to this example. Okay, so the velocity final is 60 miles per hour, and the initial, we started from 0, so we would say 0 miles per hour, and this took place in 4 seconds. So the final time was 4 seconds, and at the very beginning, before we started, it was at 0 seconds. Okay, so now this is the equivalent of 15 miles per hour per second. Okay, now we're not quite done here. We actually have to adjust this unit measure because we have a unit measure of time in hours up here and a unit measure of time in seconds down here. So we're going to go ahead and move towards miles per hour. We could calculate miles per second, but let's just stick to miles per hour. Okay, so how does this work? We're going to rewrite this unit measure as miles per hour per second. Okay, then what we're going to do is multiply this fraction by the reciprocal of seconds, so that's going to be 1 over s, and this is 1 over s. And when you do that, these cancel out, and now what we have is miles per hour second. Okay? Now, we're not quite there yet. Let's go ahead and write this out. 15 miles per hour times second. We want to convert this into hours, and the way to do that is to use the unit measure conversion that we discussed the other day. And the way to do that is we're going to multiply this fraction, okay, by the equivalent of 60 seconds per 1 minute. And we're going to also multiply this by 60 minutes per 1 hour. All right? And the reason we do this is because, watch what happens. The seconds cancel out because we have one on the top and one on the bottom. And the minutes also cancel out because we have one on the top and one on the bottom. And now what we have left is just the hours, which is exactly what we want. Okay, now if we go ahead and multiply that all out, 15 times 60 times 60, we get 54,000. And now my unit measure becomes miles per hour times hour, or miles per hour squared. Okay, so if we clean this up, we would say that this is moving at 54. The acceleration here is 54,000 miles per hour squared. Okay, so that is our acceleration. Now, the other thing I wanted to cover, and I'm going to go back to the velocity, is that we also need to understand how this works out on a graph. Okay, and here's what I mean. When we talk about velocity, we are talking about a position time graph. Position and time. Okay, so if we see something like this, see a straight line, okay, as you will notice, as the time increases, okay, as the time increases, let's say this is 1 second, my position increases, and as my time goes to 2 seconds, my position increases, and then if I go to 3 seconds, it now increases my position. So this is showing me that my velocity or my speed is moving at a constant velocity, okay? As time increases, my position increases. Now, here's another situation. So let's say that we have this scenario. Okay? What this is telling us is that my position hasn't changed. I moved away at some point, I don't know when, but at time t equal to 0, I'm at a particular position. And as time continues to move, my position doesn't change. Okay? So if I'm in a car, I'm just sitting there as time is ticking away. Now, as soon as this graph changes, okay, this tells me that at this point in time t, my car is no longer sitting still, it's moving because my clock is ticking. So I'm moving to the right, and now I'm moving. So that means I'm moving at a particular speed, and if I experience a straight line again, that tells me I've now stayed still at a new position, okay? So I was at a current position, nothing happened, I'm staying still, and as soon as I hit this time, my position changes, okay? And then once I hit this part here, this time, I now have stopped, and now I'm not moving anymore, okay? So this is a position time graph, and it's really important to understand how to interpret that. So hopefully that made sense to you. Okay, that is it for this lesson. Hopefully this made sense. If any of it was confusing, please go back to the beginning of the recording and listen to it again. Thank you.